Thank you very much for the kind introduction. So I'm excited to talk to you today about large language models. I think I may have packed a few too many slides. I will either skip some or go somewhat quickly through some parts of this. So there's two parts. There's the morning session and the afternoon one. And in the morning one, I want to go through 4 different topics. I'll give you kind of the roadmap. First, just in case you haven't been exposed to large language models recently, I want to talk to you about why I'm excited about some of the potential of this technology. Then I want to talk about language modeling, the core statistical task that I think is quite exciting and important. And then finally, I want to go through the details of neural architectures like RNNs, transformers, and then sort of start on pre-training. We don't know, or I don't know how much I'll get through that very last part, but we'll see. Okay, so to get started, language models are in the spotlight. Hopefully, all of you know this. ChatGPT is probably when these systems came onto the public mind and everyone started interacting with them. But really, going at least as far back as GPT-3, it was quite clear that there was going to be this enormous change, this revolution, at least in the field of natural language processing. The capabilities that these systems bring are pretty remarkable. I'll briefly mention some. I mean, GPT-3, this idea of in-context learning, the ability to learn without doing things like parameter updates is pretty remarkable. And with things like ChatGPT, it's quite apparent that these systems have a kind of out-of-distribution robustness that we haven't seen in many systems before. And in GPT-4, there's been claims about how good it is at certain kinds of professional exams. And so this is all a very exciting time. And if you go and look for examples of successes of this kind of language modeling paradigm, you will find quite a few remarkable ones. Everyone, I think, has their own favorite example of why language models are interesting. I think mine is often code synthesis. This is an example from Sebastian Bubek's paper, the Sparks of AGI one, in which they pulled out a couple of fun examples about what GPT-4 could do around the time of its release. And I think this one's remarkable in that it specifies basically a plotting task in which you're giving it the data and all of the detailed analyses and the way in which you're supposed to plot it. And GPT-4 does an admirable job in writing matplotlib code that produces exactly the kinds of plots that you're hoping to see from this very long set of instructions. Many mathematicians I know are very much excited about using these kinds of technologies, not necessarily to actually do the proofs, but in providing assistance for proofs. There's rudimentary capabilities that people are starting to see, like the ability to evaluate some nested functions or do some simple proofs. And people are hooking them up to sort of formal proving systems and so on and so forth. So all this is quite exciting and interesting. And underlying this, I think, is a very rapid progress in NLP and in machine learning as a whole. And I'll talk a little bit about what my view is of what drives this progress. But I do want to show you this plot by Dao Kela and colleagues that show how benchmark performance has changed over the years. So we've got very classic machine learning benchmarks, things like MNIST, the handwriting digits recognition task. We've got Switchboard, which is speech recognition. We've got ImageNet. Hopefully all of you know what that is. We've got Squad, which is question answering, 1.1 and 2.0, and we've got Glue, which is supposed to be general language understanding evaluation. So it's a meta evaluation of many different kinds of language understanding tasks. And I think the thing that's remarkable about this plot is really, these classic machine learning tasks, they've had slow and steady progress up until maybe like 2012 or so, when these systems started to reach human parity, which is the red horizontal line here. If you look at the NLP task, there's this like very fast vertical shot that goes up, and then suddenly performance is saturated and hits human level. And so part of the question is what happened here, right? What is with this remarkable improvement that's happening in these benchmarks? And I think one of the things, if you really only take away one thing in a talk or one thing in a lecture, and I always like to say this because not everyone has the ability to remember everything. I think the one thing you should remember is how dominant and how powerful pre-training is as a paradigm, at least if you're interested in sort of the empirical aspects of machine learning. As a Stanford person, I'm somewhat contractually obligated to say the word foundation models. But really, the idea is that coming up with new models and new learning approaches that can leverage vast amounts of internet data is really the key to all of this performance. And I will talk through how this sort of manifests in the language setting over the next 2 hours of lectures. But the intuition is this. Let's say you're trying to build some sort of a language system, right? A system that can, say, answer questions. It makes no sense to have the system learn like the syntax of language from scratch each time, right? When you're learning to answer questions or to do math, You're not learning things like how numbers work from scratch, right? You have a bunch of common sense from your lived experiences and your primary school education that equips you with the basic tools necessary to do the tasks, right? And pre-training in many ways is the piece that lets you do this. And so large language models, I think, is really a great illustration of this pre-trained paradigm. And so I want you to keep that in mind as I'm going through a lot more of the technical details over the next several slides. Okay, so to set the stage, I'm going to be talking about language models. And language models, I think you can conceptually think of them as coming in different pieces. And this lecture will be organized in those pieces. So a large language model really has two different steps in its training procedure. The very first one you can think of as the world's largest autocomplete system, right? So you have autocomplete systems on your phones. The task that they do is they get some sort of sequence input, right, a prefix, and they are trained to predict the next word, right? And so you build, by using scaling and deep neural network architectures, the world's largest and most powerful autocomplete system. And this is sort of the basis on which everything else is going to be built. But of course, we don't really want to just mimic users on the internet for the basis of all future language understanding systems, right? And so I think one of the insights that people have had over the last few years is this idea of taking a very large language model, this autocomplete system, and adapting it in ways that make it useful for many downstream tasks. I'm going to call it post-training. Other people call it alignment or RLHF or what have you. And that's the second piece that's going to be important, right? And so conceptually, I'm going to be talking about those two pieces. I'm going to talk about step one, which is the pre-training piece first, and then I'm going to talk about post-training afterwards in the second part of this lecture. Okay, so language modeling. Language modeling is kind of the core of large language models, right? It's right there in the name. So what is the language modeling task? The thing about language models is, unlike many of the things that I think you'll learn in the summer school, language models are conceptually extremely simple objects, right? A language model is a system, a statistical system that predicts the next word. That's all there is to it. So, you have the students open there, and then you fill in the next word. Maybe it's book, maybe it's laptops, so on and so forth, right? More formally, the task is a probabilistic modeling problem. You have a sequence like x1 through x of n, and you would like to produce the probability distribution over the next token, so x of t plus 1, where that can be any word in some very large vocabulary set v. And anything that can do this is called the language model. More precisely, it's an autoregressive language model, where the word autoregressive means it is predicting words given some sort of a prefix. It's factorized in a very specific way, just like this conditional distribution shown here. And you can also think about language models not just as predicting a next word, but it is also predicting implicitly the probability distribution over an entire sequence, right? And so as machine learning folks, I think the right mental model for this very first phase, this pre-training phase, is that it is one big probabilistic modeling problem. It's a generative modeling problem, right? So we would like to build a model of this sequence x1 through x of t. And the way in which we do it is to first factorize it into a sequence of conditionals, right? We're going to predict the first word, then we're going to predict the second word conditional to the first word, right? It's kind of an obvious fact that, because of the rules of probability, we can, of course, factorize any joint distribution into a sequence of such conditionals, right? And this is really the fact that underlies why autoregressive language models can actually capture, structure for an entire sequence, entire long-range sequence. So the starting point for language models, I'm going to build it up into pieces. Not all of you are going to be familiar with language models and sort of the history of language models. So I'm going to start very, very simple, and then I'm going to build up to what people use now, which is these big transformer architectures. And so the very starting point of a language model, I think, let's say you were asked to build a language model. What's the simplest, most basic one you could build? Well, it's just a count, right? So an n-gram language model is a counting-based language model. So if you have something like the students open their blank, right? What are we going to do? Well, we can count the number of times that certain prefixes lead to a new word, right? So what are we going to count? We're going to count n-grams, which might be a single token. That's a unigram. It might be 2 tokens in sequence. That's a bigram, and so on and so forth. And the idea here is that we're going to be doing a lot of counting of these subsequences, and we will use a particular factorization to build a probabilistic model. So what do? Well, we make a very simple Markov assumption. We basically pretend that nothing exists before the 4 most recent tokens for a 4-gram language model. Or sorry, three most recent tokens for a 4-gram language model. So we discard everything before that, pretend it doesn't exist. Now what do? Now we have these 3 tokens, and we simply count, right? So if we have students open there, let's say that occurs 1,000 times. Out of those 1,000 times, let's say it continues to books 400 times. Well, then this naive Markov model would basically say that the probability of continuing this sequence with books is 0.4, right? And if exams happened 100 times, there's a 0.1 chance of continuing that way, right? So it seems like this is a fine model, but there's a problem here, right? If we look, we discarded the word proctor, right? And the word proctor is strongly associated with exams, right? So if we didn't discard that word, we probably would have known that the word exams is a much better continuation than the word books, right? So n-gram language models have this very strong limitation. It is very myopic. It looks at very recent words. And so it can't build a very rich, powerful, probabilistic model. If we use such a language model to generate text, n-gram language models have been around for a very, very long amount of time. If you use one of those older automated speech recognition systems or machine translation systems, you probably have interacted with one of these systems in some implicit way. They're not bad. If you generate straight from an n-gram language model, you'll get surprisingly grammatical stuff, but it is often incoherent. And incoherent means that there's no long-range dependence. It has no real meaning to sort of the word salad that it's throwing out. And so now what are we going to do? Really kind of the issue here is that we know that n-grams are not a rich enough representation of language. And for a moment, let's say you put on your sort of neural network hat or deep neural network hat. Let's say you have one. Then what would you try to do? Well, we would like to move from this counting-based approach, this very rigid, non-parametric model, to something that's hopefully a more flexible, rich parametric model that we can learn from a lot of data. So the very first baby step that I want to make is to take an n-gram language model and just make it directly neural. So what are we going to do? We're going to have the same input-output type signature. So the inputs are still sequences of words, and I'm only going to look at the most recent n tokens, right? So the same inputs as an n-gram language model. And I'm going to output the probability distribution of the next word. But instead of counting, I'm going to have a neural network basically make that prediction, right? So you have all of my sequences. I'm going to concatenate them all into one big long vector. That's going to go into some multi-layer perceptron. That's going to output some vector that becomes a probability distribution, right? So this is all fairly straightforward deep neural network stuff. And more formally, you can think about this as you have a sequence of tokens represented as indicator functions. This becomes a set of embeddings, a learned embedding where each word gets a fixed vector. That's concatenated, fed into an MLP. And then there's a softmax that will give you a distribution over the vocabulary tokens. Right? So this is a very standard execution of this kind of an idea. So why is this good? Well, this is great because in a way, this improves significantly over the n-gram model, right? We don't have a sparsity problem. That is, if I don't see a word ever in the n-gram model, n-gram in the n-gram model, there's nothing I can do about it. I can never make a good prediction about that. Often people use something called a back-off and so on. The details aren't important. But basically, in order to use an n-gram model, you need to have seen all of these many different subsequences. We also don't need to store all the n-grams, which is a nice computational aspect. But there's really significant remaining problems. And I think this first remaining problem, I think, is a big one that I think you should sort of remember as we talk about neural architectures, right? Sequence modeling is all about sequential dependence, right? So when we're building out a sequence, we're generating words, right? We need to look back to the past, look at everything that's relevant, and be able to generate a probability distribution that's appropriate for the next word, right? That's sort of our goal. And so being able to depend on the past is sort of a core operation. And this MLP does nothing for us, right? Because we're only looking at a fixed size window, right? We haven't made that dependence any richer. Okay, so we can maybe enlarge the window, but we've got the same problem here. If we enlarge the window, our MLP is now operating over enormously high dimensional spaces, and we've got learning problems. We don't have enough data in the world to saturate that very complex neural model, right? And the key problem here is, in some sense, there's no symmetry. When a word appears in, say, the first position versus the last position, you never get to sort of reuse that information. The weights that I'm using are learned from scratch. So a word in position 1 means something completely different than a word in position K, right? And so there's sort of an inductive bias here that's not very good. And so this really motivated this idea of a recurrent neural network. And this is sort of the first baby step towards building effective language models. And so let's say we have an input sequence like students open there. So now we're going to take that, turn it into a one-hot vector. And then we'll embed them into embeddings just like before. And now we have a sequence of embedding vectors. And then we have a very simple computation. We take an MLP, we turn that into a set of hidden states, and then we pass things forward. And so the key trick with a recurrent neural network versus what we had before is that we're reusing the exact same computation over and over again. At each time step, I take a hidden state that came from the past, I apply some MLP to it, and then I have my inputs, my words from the current time step, and I also apply a multi-layer perceptron to that. And those two are combined to give me my current hidden state. And the same weights are reused across all time, right? So I can repeat this process forward, and at the very end, once I'm at the very last time point, now I can add a small layer at the top, and that will give me a distribution over my vocabulary elements, right? And of course, this is great. Now I have this whole rich distribution over vocabulary. I'm probably putting probability mass on relevant words like the students open their books or laptops or what have you. This solves the key problem that we had with this sort of n-gram-like window-based neural model. Now we can process sequences of any length, right? We have this hidden state that's being passed from infinitely far in the past to the present time. And in principle, this means that you could have information that's propagated all the way through the sequence. That's great. The computation at some step t can now sort of propagate information from the past. That's great too. And the model size doesn't increase. The key thing about an RNN is that you're reusing the same operation at each time step, right? It's kind of like this dynamical system where the dynamics are fixed. And because of that, no matter how long your sequence is, the learning problem stays the same. You're still trying to learn this one time step update that's shared across all time. And that now makes learning very, very tractable. Since all the weights are shared across all the different time steps, now there's this notion of symmetry, right? If you're doing, say, sentiment prediction task, does this piece of text encode positive feelings or negative feelings? If you're doing that kind of a task, of course, if I say the word good anywhere in the past, that's probably relevant, right? So you can encode these kinds of symmetries and invariances very naturally in an RNN. Unfortunately, there's many major disadvantages. And this is part of the reason why RNNs have sort of fallen out of favor for many years, only recently coming back maybe into the spotlight. The big problem is that recurrent computations are very, very slow. It is difficult to parallelize. I think if you're coming from like a more theory or like statistical background, stats ML view, computation isn't really high on your mind. But if we're thinking about language models, as I'll show you later in this lecture, computation is everything, right? Your ability to compute or to train models very quickly is sort of critical to building good language models. And so recurrent computations are inherently serial. In order to do a computation, you have to have computed everything before it, right? And that turns into have big implications for our ability to use accelerators like GPUs. I'll talk about that a bit later. And then another issue is that even though RNNs in principle could access information very far in the past, in practice it is really difficult to train good RNNs that can do this. Training a language model, an RNN language model or any other kind of language model is actually a pretty simple affair. As I said before, conceptually, language modeling is actually very, very simple. The devil is just really in the details of how you actually get this thing to be sufficiently big and performant that it works. So if we're training an RNN language model, how do we do this? We have a sequence of words, x1 through x of t, and we're going to feed it into an RNN language model. And now, what is the output of an RNN language model? It is a distribution, right? So at each time point, it will emit a distribution over words that is likely to appear at the next time step, right? Let's call that y hat of t. Now, the loss function that we're looking for is we're looking for a cross entropy, right, between y of t, the true observed token, and y hat of t, the distribution over the my predictions of tokens. So this is just a log loss, right? Up to constant terms, this is the same as a KL divergence, right? So this is exactly solving the problem I told you before, which is trying to fit the generative model after we sort of factorize it in this very natural autoregressive way. So, in the end, what do we get? We get this term on the very bottom. It's the sum of the log of the y hats of the tokens that we see, right? So this is exactly, if you're doing log likelihood maximization on a probabilistic model that you factorize in this like time step based way, you get exactly this objective, right? So there's nothing complicated here at all. When you evaluate language models, there is a kind of a wrinkle. I think originally you might think, okay, if you're comparing two language models, let's just report, the cross entropies, right? That's what we're optimizing. But for historical reasons, that is not what people report, right? If you're evaluating a language model, actually what you report are called perplexities. And perplexities are monotone with respect to per token cross entropies, but they are not the same. So what you actually do is you can think about this. I show this in the second equation on this slide here. You're actually exponentiating the per token cross entropy. And you might wonder, like, why in the world would you do this, right? Like, why would you exponentiate the loss that you optimized? And the reason is kind of simple. It's because it puts sort of the losses in a kind of natural unit. So if you had a perplexity of, let's say, 6, what your model's doing is it's equivalent to sort of making a guess on a 6-sided dice, right? It's like the number of guesses that you have to make before you, in expectation, get a correct guess, right? And in the early days of AI, in the early days of AI and language modeling, when people were still skeptical about things like information theory, it turned out that things like number of guesses was a much more palatable metric by which to evaluate some of these systems. So Fred Jelinek was the one that sort of introduced these ideas, and sort of this choice of using perplexity sort of stuck in the field. So now you know what that is. Just to give you a sense, I've talked to you about 5-gram models. I've talked to you about RNNs. It turns out that slow and steady engineering of these systems have led to enormous improvements in perplexity, right? 5-gram models. This is from a few years back. This is the 1 billion word benchmark for language modeling. So a 5-gram model gets a perplexity of about 67.6. You can think about this in the units of bits, if you would like, or nats. An RNN-based language model, can get to something like 50s. An LSTM, which I'm not going to talk to you about, but you should think of as a fancy RNN, will get you down to like the 30s, and so on and so forth. So you can get quite low perplexities. And nowadays, if you're using these like huge transformers with big amounts of pre-training, you can get to like tens of perplexities. The progress here has been quite staggering. So, I've talked to you about RNNs, and this is great, but this is not for the most part, what we use to build large language models today. I've told you about RNNs because they're A, historically important, and B, they're important for another reason. There's been a very recent, in the last year or so, trend by several researchers building what they call state space models, which are essentially a renewed version of this idea. So they might become important again. But the problem with RNNs is that it's very hard to have this kind of dynamical system and have the optimization dynamics be stable. People call this either vanishing or exploding gradients. I'll give you kind of an intuitive idea. I won't go into too much detail in the interest of time. If we're talking about vanishing gradients, think about sort of the gradient computations for each of the parameters through the RNN. When we're taking these gradients, right, we have the chain rule. And when we compute the chain rule, we have these partial derivatives. And because the RNN shares parameters, in some sense, you're multiplying by the same partials over and over again, right? Like the partial of h of 4, let's say, over h of 3, right? This is how the hidden state at time step 4 changes as a function of the hidden state at time step 3, right? And so if this function, this is controlled by the weight matrix W, and if this is less than 1, you're multiplying your gradients by a number that's less than 1 many, many, many times. So the gradients will exponentially vanish to 0. And you can show this formally. Like imagine that our RNNs had no nonlinearity. Then it's a bunch of linear matrix multiplies. And using sort of eigenvectors, we can compute exactly what the gradients will be when we propagate them back through time. And in fact, they'll vanish exponentially quickly as a function of sort of the spectral norm of the weights. So why is this a problem? This is a problem because in practice, RNNs and LSTMs, they don't really pay attention to tokens very far back in the past. RNNs maybe pay attention to like 3 to 5 tokens in the past. LSTMs and fancy variants, they maybe pay attention to something like 12 plus tokens. These are all hand-wavy statements, but they should give you a flavor of the empirics at play here, right? Getting long-range dependence past that gets very difficult because of these optimization dynamics problems. And so these problems motivate, I would argue, sort of like a very fundamentally different approach to building language models. And this is going to build up to the transformer, which is the sort of building block for almost all of the high performance LLMs today. And so this idea that I was telling you about, about this vanishing gradients, you should think about as abstractly, how many computations does it take for sort of 2 pieces of information to interact? I'm going to give you the hand-wavy intuition first, and then I'll give you the model after. So, if I'm trying to do next word prediction on this very long sequence, the chef who ... was X, right? So this, next token X, it has to probably reference chef, right? But that information might be very far in the past. If I have a long clause in the middle, I need to retain that information all the way through with this RNN. And so, that may be very difficult. It might be really difficult to pass this information without having it sort of vanish in the same way that I talked about before. The other issue with recurrence is the lack of parallelizability. And this one hurts quite a bit. This is really difficult in practice to deal with. If we think about how we compute all of the activations of an RNN, we have to move sort of lockstep in sequence from left to right, right? So if I have this very long sequence and I want to compute, the next token, first I have to process the leftmost token, and then after processing that, I can process the next token, right? And so you can kind of see these numbers on these blocks here. This is sort of the time step at which you can finally compute the hidden state. So I can compute the first hidden state at the bottom left at time step 0, and then I can compute its neighbors at time step 1, and then time step 2 afterwards, right? These are all serial operations. And that's really terrible because in some sense, the ability to use large-scale parallel matrix multiplies is what powers things like large language models. You might not appreciate this quite yet right now, but I'm going to talk about scaling laws in sort of the next part of this lecture. And there, hopefully, you'll appreciate how important it is to be compute efficient when building these things. And so RNNs, just to sort of recap this, not terribly compute efficient due to the lack of parallelizability. So attention is the thing that provides a solution to the bottleneck problem. And I think in some ways, for neural network architectures, attention has been sort of the single most impactful thing that's happened. So the core idea is instead of having this recurrent connection where the hidden states of a neural network are passing information forward, let's just have direct connections, right? At time step t, I'm going to directly have a dependence on every token in the past in a particular structured way. And that's this idea of attention. And so we'll show you this via diagram first. So to get an intuition of attention, at least as a machine learning person, when I first saw the attention equations, I was like, this makes no sense to me. But actually now I think it makes a lot more sense to me if we start from this perspective of mean pooling, right? In a recurrent neural network, right, we're basically passing information from left to right in this sequence, right? And what we would like to do is to be able to depend on information along the entire length of this sequence, right? So what's an operation that allows you to do that? That allows you to take information from anywhere and then make use of it, right? Well, a really easy way to do that is just to take the mean, right? If you take the mean of all of your hidden states, right, that's obviously aggregated all the information at once in a kind of indiscriminate way, of course, but it's taken all the information, right? And so this is kind of the starting point for the idea of attention. Like we can take a mean pool or a mean over all of the hidden states, but do it in a slightly smarter way. And so attention is just a weighted mean, right? And we're just going to compute the weights using a particular neural network, right? And that choice of a neural network may or may not be important. But the point here is that it's a slightly important averaging operation. And so you can think about attention as a weighted mean in which we've computed some weights over each position. And we're going to do that through something called keys and values. And the reason to do that is because we want our attention to be able to approximate sort of a hard lookup table if we want to, right? So we might have in a lookup table, a key and a value, and if they match exactly, then you retrieve just that element, right? So we will build sort of this averaging operation that can emulate that, as well as emulate sort of just pure averaging if we want to. So what does that look like? Well, so the core idea here is if we're trying to predict, a next word. So let's say I'm doing machine translation. I want to look at sort of my source sequences, and I'd like to produce my next word. What am I going to do? Well, I'm going to have a direct connection from where I am. So I'm at the start token right now. I'm going to take inner products with the embeddings of each of the source sentence tokens. So I'll take an inner product between the start and the first word eel. And then I'll do the same thing with the second word, storing essentially the results of all these dot products, right? So I'll take a dot product for each position of the input sequence, or if you're generating maybe your prefix. Now, what do I do with these dot products? Well, I have a dot product, which is a real valued value. I can just take a softmax over these, and that will turn that into a distribution, right? Now it'll normalize to 1. I have these weights. I'm going to call this the attention distribution. And now, we can think about this maybe as kind of an importance. Not quite exactly, but maybe. And so what we can do is we can look at this very first position, he, that's the most important one for this word. And now that can be the attention output. I'm going to take the weighted average of all of the sort of embeddings that I have with this weighting distribution, right? And so, this should make you think about what I said at the very beginning of this part, which is it's just like an average, but we're doing weighted averaging where the weights are determined by this very structured operation, this inner product between my current position and everything that I might be paying attention to, right? And so now it's just the weighted sum. This is all very straightforward stuff. And this output can go wherever you want, right? This can be fed into part of an MLP to give you the next positions distribution, right? And that's exactly what we're going to do to get the distribution of the very first token. Okay. And we can repeat this over all the different positions to give us our entire sequence. I'll skip over this in the interest of time. And so in equations, this is also pretty simple. We have some sort of, let's say, encoder hidden states or hidden states of my prefix that I'm trying to generate from. I have a position that I'm trying to generate from that's S of t. And then I'm going to take an inner product between my decoder hidden state and all of my encoder hidden state. These dot products are exactly sort of the dots that you saw in the previous slide on the left side, right? I'm taking dot products to tell me how important each position is. And I'll take a softmax, which gives me a distribution over these positions. And then I'll take a weighted average to give me sort of which information I should be propagating to the next time step, right? And finally, we can either concatenate this or sort of add it into the MLP. I'll talk a little bit about some of those design decisions in a moment. And attention is really one of these operations that works incredibly well in practice. It was originally developed in machine translation, where I was showing you that example before. It makes a lot of sense. If you're translating between two languages, often what you want to do is pay attention to a very particular word and then translate that word in context, right? But it's turned out that attention is really, really useful for just building things like language models in general, right? It's not just a translation thing. It's a generically useful tool to build sequence models. And that's where we're going to go to sort of next. But to go through this specifically, right, it solves sort of this bottleneck problem that you might have. In the past for RNNs, you had to pass everything through a hidden state. And that was very challenging. You had to have these very complex gating mechanisms and so on to make sure that your information was sort of kept across all time. It solves the vanishing gradient problem. In a way, you can think about vanishing gradients as the difficulties that happen when your loss and your sort of inputs have many, many steps of computation between them, right? And attention, in some sense, makes direct connections between the outputs and your inputs, right? At each time step, you're directly sort of paying attention to all of the positions through this inner product. And then finally, something that a lot of the interpretability people have made a lot of use of is that attention maps are often interpretable. They're weighted averages, which maybe makes you think that you can actually understand what's going on inside these attention operations. In fact, in machine translation, that's often the case. If you look at sort of these attention maps for translation systems, you'll actually find that when you're translating certain words, you're actually paying attention to the corresponding word in the source language. So there's this very nice sort of human translation-like analogy that's actually going on here. Okay, so now I think we get to the core sort of idea or the core thing about the transformer, right? So attention was originally built as this tool to help with machine translation problems. And then people started to realize, actually, hey, attention is just useful for any kind of sequence generation problem. You have an RNN, you put an attention piece there to be able to pay more attention to the input, works better, right? Some folks at Google then started to think, actually, can we just use attention everywhere? Can we get rid of the recurrent piece entirely? Because that leads to many problems, like the vanishing gradient problems, and so on and so forth. And so this is kind of the idea that instead of using a recurrent sort of hidden state to pass information forward, what we're going to do is that we're going to use attention everywhere to do the same thing. And so that's kind of the success of the transformer comes from this idea that we were able to get rid of the recurrence entirely. Okay, so the example that I showed you before, and also machine translation, if you have that sort of mental model in your head, that's called cross attention. Cross attention is when you have some sort of generation system, and that's paying attention to various parts of your input. But what we're going to need is something that people call self-attention. When you're generating tokens one at a time in a sequence, this is what people call decoder-only models. You need something slightly different. I'll go over the engineering decisions and the choices that you need to enable that in a moment here. But just to be clear, what does self-attention look like? I think there's a very intuitive idea of why self-attention is a pretty straightforward idea that works for language modeling. Let's say I have an example like I went to Stanford CS 224N and learned blank. This example, of course, I took the slides from 224N. That's why it's specialized to that one. In this case, right, the attention weights for learned, right, the word that this is relevant for is you might pay attention to the word CS. You might pay attention to the word Stanford, right? Because you want to know what classes you're sort of going to be generating about, right? So what is the thing that you learned? What's relevant for that? Well, obviously the place, the university, and the course number and the topic, right? And so the attention weights can sort of tell you which words are relevant for generation. Self-attention is basically just attention, but with slightly different pieces. I'll give you the notation for attention now in sort of more precise detail. This is how people write it for the transformer, for various other transformer implementations you might see. And so I'll just sort of go through it in a little bit more detail. So let's say we have a sequence of words, W1 through Wn, right? So this is your kind of prefix. This is what you're getting as input. Now what I'm going to do is I'm going to embed each of those. So the x's are sort of vector embedding. So they're lower dimensional objects. So the x's are each, one hot encoding. So they're, one in the position where the vocabulary element is and 0 elsewhere. Now we take these embeddings and we transform them into 3 different ways. We transform them into queries, keys, and values. We've already seen through the diagram and various examples what that looks like, but I'm going to talk you through all of these once again. So a query, you should mentally think of as a lookup, right? So here, let's say you're generating a sequence, and you know that you're looking for an adjective, right? You know that the next word is going to be an adjective like good or bad or whatever. Now, for this adjective, you're looking for sort of like a noun in the past. So Q, the query might be like, what's a noun that happened in the past, right? Or what's a relevant person name that happened in the past. So query looks up things like that. A key, right, is a linear transformation of this embedding as well. These are basically for each of the positions, what attributes exist, right? So K of I is the key for this particular position, and the value is the value that you're going to be averaging. So this is slightly different than the attention example I gave you before, where sort of the keys and the values were exactly the same. So the idea here is very simple. I'm going to go through for each position, for each ij, so for each pair in my sequence, I'm going to compute eij. So this is the dot products in the diagram. So here for position I, the query at position I, what are the relevant possible places to take information from? Those are positions j. So qi.kj, this is essentially the dot product that tells us how much to weight a particular position. And of course, we want a distribution over position. So I'm going to normalize that through this softmax. Now for each position now, what I'm going to do is going to average over the values using these weights alpha ij as a weight over the different positions. Right? So this is the same idea as before, just more formal in equation form. What's the problem with just naively using this as the building block of a neural network architecture? There's going to be 3 problems. I'll talk about each one in turn. The first one is that attention doesn't have an inherent notion of ordering. And this is kind of a big problem because we know that language has ordering. When I'm generating the next token, it's important what order the words I saw were in. And so what do I do? Well, all of these models use not quite a hack, but a simple trick. So it's called sort of position embeddings. Attention itself is just a whole bunch of dot products, and dot products don't have positional dependence, right? It doesn't matter where you had the dot product. And so what people do is they take something like a position vector. So P of I here represents the position of token I, and P of I might be many different things. People might use P of I as sort of sines and cosines, where the values of the sines and cosines tell you where you are. They might also be a learned embedding. So for example, PI is itself a parameter where there's a value for each possible position that you're in a sequence. And so in this case, we have a value like a parameter, let's say, for each position I, and I just add it into our embedding. So the actual final token embedding is my original token embedding X of I plus a position embedding P of I. And of course, you could do things like concatenation, but in practice, everyone just adds the position embedding into this thing. So there's many different ways to do position embeddings, but I'll just give you one really simple one. And the simple one is to just let all of the PIs be learnable parameters. This is in some sense the maximally deep neural network learn everything idea. So here we're learning a matrix, which is D, which is the embedding dimension, and N, which is the maximum sequence length that you might possibly want to ever generate. And we just learned this entire matrix. So each column of this matrix is sort of an embedding corresponding to a position, right? It's basically saying, if I map position 1, add this vector into the embedding. This has, each position gets to fit its own data. This is maximally flexible. It has the con that it will never extrapolate outside the sequence. Models built in this way, like BERT, which was an older pre-trained model, they're sort of fixed in the size of their window. You can never go beyond that. And if you ever want to deal with longer sequences, you just have to truncate it. Okay, so the solution to ordering is just to add a position vector to each position that lets us know where the token is. The second problem is if we're building an architecture for sequence modeling, you can't just have this linear matrix multiply. You need more pieces to it, right? We need a bunch of flexible nonlinearities and so on. And so what people actually do is you have this sort of self-attention, which is this key value, key query value triple, right? Which lets you basically propagate information from one position to another. But you follow that up at each position with a feed-forward network. A very large feed-forward network, often actually. This is most of the parameters in a large language model. And so the feed-forward network allows you to perform some additional computation to have a richer function class that takes all of this information that's been sort of linearly interacted and sort of process it in a way that allows you to model more complex distributions. There's been a lot of work studying what each of the components of the transformer actually does. A folk theorem that people say is that essentially the feed-forward computation is in some sense one of the most important pieces. If you have a large language model like say GPT-3 or ChatGPT, it often turns out that the piece that does things like memorize facts is actually in the MLP and not in any of the self-attention layers. So it serves quite an important role, and without this nonlinearity, essentially the whole thing would really not work. A final problem here is that attention computations, in some sense, if you want to do it in a parallel way, inherently look at the future. That might be a little bit of an odd thing to say. So maybe look back at, sorry, I'll go back a few slides. Let's go back to this slide over here. When we're doing the attention computation, this is the middle equation here, EIJ, right? This is a big inner product between a matrix Q and a matrix K, right? But what's happening here is that you're taking all of these products between, if I'm at position T, I'm also taking inner products with positions that are future to T. And that turns out to be a big problem. If I take the distribution, I'm averaging over values in the future. So that's really bad, because if I want to parallelize, it basically means that I can't use this kind of nice operation. And so there's a computational trick that's very useful that I will highlight. It's a very short one. So what you end up doing is that you first compute that EIJ matrix by taking a big inner product between queries and keys. So that's what you see at the very bottom here. But actually, when you're looking at positions that are in the future, you actually add sort of a negative infinity to that matrix. You call this sort of a masking matrix. It's an upper triangular matrix where the upper triangular elements are all filled with negative infinities. And what's the reason for that? They're basically positions that you're not allowed to pay attention to. So if you look at the very first row, we're at the start token. We haven't generated any words yet. And so I don't know anything about the future. And so every token in the future is masked out with a negative infinity. If I'm in the second position, which is the second row here, I'm generating, I have the word the, and the only thing I know is that the start position was kind of to my left, and I know that the is my current token, right? And so I can look at those two things and can't look at anything else in the future, right? So they're masked by negative infinity. Of course, you can do things very naively to avoid this masking trick, but the key thing, once again, that I want to drill into you is how important computation is, right? And so if you do this masking trick, you can do all of these operations in big matrix multiplies and big matrix additions. That turns out to be incredibly efficient on a modern GPU. Okay, so there were 3 barriers to building a sequence model out of attention operations. We have solved all of them, right? So there was a problem with no inherent notion of order. Solution is to add a position embedding. There was a problem that you can't just build a neural network out of just attention, so you add feed-forward layers. And then we need to make sure that we can compute these things in parallel without doing things like looking in the future. And we do that through this masking trick. And so that really just basically gives you what you might call like a self-attention block. So you have your inputs, right, your sequence, you embed those, you add position embeddings, you do that at the very bottom, and then you repeat this operation over and over again where you have self-attention. This masking part is exactly this adding negative infinity trick I told you about. And you have this feed-forward layer in order to make the function class more flexible. You repeat this operation multiple times. A typical number of layers for a transformer is like 12 to 24. And then you have a linear layer on top, and you have a softmax that turns the output into a distribution over your vocabulary, right? And this is basically almost the transformer, almost. This is like 95% of the way there. So what's left? I won't cover these pieces because they're conceptually very similar to the pieces I covered, and I don't want this to turn into a full-on, how do you make deep neural network architectures for LMs. There's things called multi-head attention. You can think about this as you have more than one attention head. It's not too hard. You have residual connections, which you can think of as instead of having the feed-forward network, you have a feed-forward network plus the original input signal. So you're modeling the residual rather than modeling the entire function. And then finally, a thing called layer norm, which standardizes each sort of it standardizes activations over the hidden dimension. The details here aren't important, but it is practically important in order to make the neural network train nicely. And actually, all of these final sort of details give you the entire transformer decoder block. And this is exactly the original transformer implementation. You basically have, once again, embeddings, position embeddings. You have masked multi-head attention. And then add plus norm, that operation is basically the combination of a layer norm and this addition piece. You see this arrow that goes around the multi-head attention. That's what's called a residual connection. And we have the same sort of operation at the feed forward, right? So this is conceptually not very different than the easy version that I told you about before. And hopefully that gives you intuition about how transformers work, right? Now you know about how attention works. Now you know how to do masking and parallelization of all these operations. The only things really missing is things like residual connections and layer norm. So hopefully that's kind of clear. Okay, so I want to spend the last few minutes talking about pre-training. So why is the transformer architecture so kind of important? I think sort of the two go hand in hand. Of course, the transformer turned out to be a really effective architecture for things like translation and so on. But I think the reason why transformers have become so widely used in so many different fields is because it can often be coupled very effectively with pre-training. So I showed you this plot before of benchmark performance is sort of saturating very quickly. That's coming from pre-training. If you look at any individual benchmark like squad, you'll see like this big bump around 2018, which is when some of the first pre-trained models started coming out, the BERT model. And as I get into pre-training, I'm going to talk about this much more in the second half of the lecture. But pre-training is all about scaling unsupervised learning on the internet, right? Like the key idea, of course, is that the internet is this enormous wealth of information that's available for free, right? If that's sort of a very AI term, but imagine you're a Bayesian, right? It's like a free source of an empirically driven prior that you can use for many of your tasks. It's sort of foolish to not leverage as much of that as you can. And so the key here, like what makes a model or a setting good at pre-training? Well, you need to make sure that your model can scale and process enormous amounts of diverse data. Transformers are very good at that. You can't use any labeled data, right? Because labeled data does not scale. Labeled data doesn't allow you to process, let's say, all of the internet. And so you have to have an unsupervised learning approach, which is very much this language modeling thing that I'm telling you about here. And then finally, we need to be very, very compute aware. The amount of data on the internet is vast. Of course, once you start filtering it, it's a little bit less vast, but the computational challenges here are truly, truly immense. And so models that don't have favorable computation properties are just not even candidates as good language models. And sort of as I sort of leave you here for the next part of the lecture, I want to have a few minutes to be able to answer questions. I want you to think about pre-training and language modeling and what you get out of it. So what kinds of things do you learn from pre-training, right? You kind of think about language modeling, and I think the first reaction most people have is, oh yeah, great, you can generate text now. Wow. But actually, it turns out that the ability to generate text gives you a ton of different things. I'm giving you a few examples here. So you might have like Stanford University is located in blank, California, right? If you can fill in the blank, you know something about Stanford University in California. If you have, I put blank fork on the table, they'll tell you about syntax. The woman walked across the street checking for traffic over blank shoulder. Well, whose shoulder, right? It's the woman's shoulder. And so you learn about co-reference, right? So you can look at each of these examples. I won't read them out loud for you. But you should see that the ability to fill in the blank and generate text is an incredibly powerful primitive that forces a model to learn a lot of different things about the world through the internet. And so I'll leave you here. I've got a few more slides, but I'll get back to them afterwards so that I can answer some of the questions that may have come up. Okay, welcome back, everyone. So in the first part of the lecture, I covered sort of a couple of things, the basics of language modeling, neural network architectures. And now I think we're going to get into the part that's really about like large language models in many different ways. The first thing I'm going to cover is pre-training. In my opinion, this is one of the most sort of impactful things to happen in empirical, definitely NLP, maybe also machine learning over the last few years. And so I want to talk through that somewhat slowly and carefully. And afterwards, I want to talk about post-training. This is a lot of what happens where, after people build these very large pre-trained models, they adapt them to be usable for downstream tasks. Things like ChatGPT are built through this post-training process. And then finally, I think, a lot of my lecture has very much been about, deep neural networks, engineering, throughput, scaling. And I want to connect it a little bit back to statistical machine learning. After all, it is the machine learning summer school, not the deep learning summer school. And so I'll talk a little bit about some of the connections between the two, interspersing some of the research that we've been doing. Okay, so to get started, pre-training is this idea that you really want to be doing a downstream task. You might want to be answering questions. You might want to be analyzing sentiment. But before we do that, what we're going to do is we're going to first do a different task. We're going to do a pre-training task. So one of the earlier works in this line of thinking is Dai and Kwok's Lei, 2015, who showed that if you first train this autoregressive language model, so that's what we spent the first part of this lecture talking about, and then afterwards you do a bit of fine tuning to adapt this model to a downstream task, this works exceptionally well. In a way, this idea forms the foundation of a lot of what came after it. And so just to explain the idea, what you first do is you first do a language modeling task. That's exactly the next token prediction generative modeling task that I mentioned before. And of course, there's a ton of data for this, right? So this pre-trained model is going to be quite good. It will be an amazingly good generative model of predicting the next token. And now, after we do that, we're going to save the neural network parameters that we had, and then we are going to be fine-tuning it. We're going to take this neural network parameter, use it as initialization, and then we will make our prediction for the downstream task. If we want to do a classification task, maybe we will add a linear layer or a linear classifier on the very end of our neural network, and then fine-tune the whole model, that is, take gradient steps against the downstream task loss. Right? And the realization was that pre-trained models through language modeling serve as an extremely useful initialization. I'm not going to go into other kinds of pre-trained models. BERT was a different class of pre-trained models that was extremely popular a few years ago. It's still popular in many NLP tasks, but it is quite different from a lot of systems that we have today, like these ChatGPT style systems. I won't go into very much detail. I'm going to focus on pre-training through language modeling. And there's been quite a bit of sort of theory and thinking about this class of topics. I don't really want to go deep into transfer learning theory or to try to explain or justify to you why this paradigm works. And part of it, I think, is still an open question. So why does pre-training and fine-tuning help, right? I think an argument that's commonly advanced in sort of the theoretical analysis of these kinds of approaches is that, first you have some pre-training loss, in this case, language modeling. That's very useful. You can train this thing to optimality because you have tons of data, and you can train a very big model on this. Next, what you want to do is actually train your model on the fine-tuning loss, right? And because you're initializing at the pre-trained loss, you can think of it as you're implicitly regularizing the solution of this final objective towards the initial point of your pre-trained loss. And because we're using things like SGD, we have this implicit regularization effect. And as long as pre-training serves as a useful initialization, we have good inductive biases for the downstream task. Empirically, this has been one of the most effective single interventions that has happened. And for a while, pre-training sort of advanced in a very different direction. Initially, Dai and Lei produced this idea of using language modeling to pre-train. And then other folks from Google invented BERT, which uses a different objective. And people moved away from these what people call decoding-based approaches. But actually, now the recent systems like ChatGPT have returned to this language modeling-based objective. And so now we can talk about that here. So if we have a pre-trained decoder, that is, we have a language model that's been trained on enormous amounts of internet text, and it's very good at predicting the next token, what you can now do is you can, of course, if you have a text generation task, you can fine-tune it to do that text generation task, right? That's a very natural matched objective. You pre-train the model to generate text, and then you can fine-tune the model to continue to generate text. And this is great if you're going to be generating something like, or making something like a dialogue system, right? You have text in, text out. That's very much the format that a language model might see. If you're doing summarization, that's also very easy, right? You have an input that is an article, and then you're generating text that is the summarized version of this article. So in both of these cases, you have a very simple way of adapting a model for this downstream task. And this is about the sort of paradigm that was very dominant around the era of GPT-2. OpenAI, built several generations, I will call it, of larger and larger language models. And I think it became increasingly more apparent how sort of powerful and useful this paradigm was. And so with GPT-2 back in 2018, what OpenAI demonstrated, and several others started to demonstrate around this time, is that pre-training was very useful for building effective text generators. And this example, this excerpt that I'm showing here from the original sort of release announcement for that model is, if you follow text generation literature at all, is a very famous sort of passage about this. You have an input that's a part of an article at the very top, and the language model completes it on the bottom half. And it's generated sort of this convincing looking article, fanciful article about the discovery of some new species called Ovid's unicorn, right? And this made it clear that pre-training was going to be a really effective part of any kind of text generation task in the future, right? This kind of text generation quality was in some sense unheard of before GPT-2. And so that demonstrated sort of the effectiveness of this approach. I think the thing that has really changed the game was, before, pre-training a decoder-only language model and these transformers was very much a thing that was of niche interest. People who are interested in generating text were very excited about this paradigm, including myself back when GPT-2 came out. But I think a lot of people care about different kinds of tasks. Maybe you care about question answering. Maybe you care about sentiment prediction. And it wasn't really clear how language models were going to be important in those kinds of tasks. And I think I said at the very beginning of this lecture that GPT-3 in some sense was the starting point of when language models became really, really sort of unique and interesting. And the reason why that's true is because I think GPT-3 started to demonstrate something different than just generating text. So I'll go over that in this slide. With GPT-2, really it was sort of a continuation of this idea of generating text. You had some inputs, you were generating text on the output side. And so what you might do is you might fine-tune models, you might build these sort of classification layers. It was this very traditional paradigm for machine learning. But with GPT-3, there was this sort of very intriguing empirical phenomena that started to be demonstrated. And it was this idea of adapting to a task without ever updating the parameters of a model, an approach that often people now call in-context learning. The idea here is that if you put into sort of the prefix of a language model input-output pairs, then the continuations in the future would sort of mimic this task. I'll show you an example next. But I think what this started to show was that these decoder-only language models, these models that were trained just to generate text, could actually be useful in many more ways than just to generate text. And of course, to achieve this, you need these enormous models trained on enormous numbers of tokens. So GPT-3 has 175 billion parameters. Most of you are probably not training models of that size. And in context learning, I think it was, to me, a very intriguing phenomenon, because it behaves in sort of a very different kind of learning mode. I think most of us are used to sort of training models by, say, updating parameters or finding some parameter that optimizes some objective. That's really how we think about sort of statistical learning in its most basic form. But within context learning, what's kind of happening, you can kind of think this as, many people think of this as a form of Bayesian inference, right? In your inputs, you're putting in part of a task, the training data set, in a sense. And then the model, performs a kind of posterior inference of what's the most likely sequence to follow given this input. And so there's implicitly something that looks like learning happening, even though all that is actually being executed by the model is sort of next token prediction. And so to give an example, right, if I give sort of pairs of English and French words in sequence, and I sort of feed that into the prompt or the prefix of a language model, and then I give it a new French word, the continuation is likely going to be its translation, right? So the language model is in some sense picking up the pattern, and to fill in the blank right after this token, the best way to do it is to actually do the task, right? This is another example of this power of basically being able to complete the next token or fill in the blank at sufficient sort of power and scale and generality, right? Hopefully you see that. And so this, I think, is a very unique and interesting thing. If you're interested in, say, robustness, it's very interesting because it means that the model has a lot of tasks within it. Maybe it's able to extrapolate to new tasks. If you're sort of interested in learning, it's also interesting because it's learning without an explicit objective or anything of that form. And so, you can do arithmetic in this way, where you give it a bunch of arithmetic examples and have it complete the next token. You can have it do sort of misspelling correction, which is in the middle, or this translation example on the right. So in all of these cases, by simply giving examples of input and output pairs, you can get the language model to start to do downstream tasks And this really opens the door to using these kinds of pre-trained models in much broader settings than just sort of, say, making continuations of funny news articles. And so, what underlies these kinds of capabilities? For a lot of the pre-training part of this lecture, what I'm going to focus on is this idea of scale, because scale is kind of a real sort of fact of life with these models, that you need significantly larger models and significant amounts of data in order to get these models to do things like in-context learning. So this is sort of a chart of all the models that people are training. I guess especially for language, you see that as time goes on the x-axis, these models are getting bigger and bigger and bigger, at least the published ones that we know about. And of course, these models are also trained on more and more data. We've got BERT, which was a model that I mentioned to you before. Roberta is sort of a generation after that. GPT-3 was supposedly trained on 200 billion tokens. Chinchilla, which I'll talk about in a few more slides, is 1.4 trillion tokens. And actually, like 1 or 2 trillion tokens now is kind of routine. If you've heard about models like Llama or Mistral or these language models that people are releasing today, they're routinely training on something like 1 to 6 trillion tokens. And so models today are using enormous amounts of data. It's using larger and larger models. And it turns out this is kind of the key to performance. I'll show you some sort of precise empirical statements that back that sort of claim up. And of course, on the very left, is human. Humans use very, very, very little data in order to get very advanced language capabilities. So there's a really remaining interesting open empirical question of like, why do humans only need less than 100 million tokens, and why does a language model trained on 5 trillion tokens not do really well on some tasks? Another sort of thing that I want to talk about sort of briefly before I get into some of the details about scaling and scaling laws is about data. I don't know if many of you actually know about what goes into a language model or what this data looks like, but it's actually pretty interesting to sort of see. This is an example of a pre-training data set. This one's the Pile, which is an open source, sort of widely available, or used to be widely available, pre-training corpus. And you can kind of see different blocks, these different colored blocks, which represent different categories of texts. The blue one is academic text. It has things like PubMed Central, Archive, Free Law, patents, NIH documents. The green one is web scrapes. It has Common Crawl, which is like all sorts of stuff that a web crawler can get to. It's got Open Web Text 2, which is outbound links from Reddit. It's got Stack Exchange and Wikipedia. You've got in orange, these are things like books, like Bibliotheque, I think, is like actually pirated books, which is why this data set is now banned. The gray one is code and math. It's got GitHub and math problems. And the yellow one is conversational text, things like subtitles, YouTube captions, and so on and so forth. So it's actually got this huge range of data. And I was telling you before, the key thing for these models is to be able to complete the blank in a huge different range of environments. And key to that, in some sense, is the diversity of data and the quantity of data that goes into these systems. So that's sort of good to keep in mind that it's not really just magic. It's on the back of an enormous, diverse pre-training data distribution. Okay. So, I've been talking to you about scale, like big models. They work really well, and they use lots of data, right? But I think the reason why scaling has been so effective and why many people continue to think that scaling will continue to be effective in the next few years is a series of empirical observations that people call scaling laws. These things actually really intrigue me, so I'm going to spend a decent number of slides talking about scaling laws. I think they're one of the most interesting empirical phenomena in large language models today. So this figure that I'm showing you here, this is from Kaplan, I think in 2020, neural scaling laws for language models. And they make an interesting empirical observation. On the x-axis is the log of the compute on the leftmost panel. The middle one is log of data set size, and the right one is log of parameter count. The y-axis in all of these is the log of the test loss, the log of the cross entropy. And you see something, in my opinion, pretty striking, which is a very strong linear trend between these quantities in the log-log plot. And because these quantities are so linear, for example, you might expect that as you increase sort of data set size or compute or parameters, you will see very predictable gains. And I think these scaling laws are a big part of why a lot of these large companies are continuing to be able to be very confident and invest in larger scale compute and larger scale data collection because of sort of empirical observations like this. And so you might be, interested in scaling laws and like, why do we have these relationships? I want to talk through a few things and show you that these are maybe to some extent things that you really already understand, and other parts of it are less so. So I want to focus on the data part of this, right? So a data scaling law is something like on the x-axis, you've got log of the amount of data. On the y-axis, you've got log of excess error or log of error, whatever metrics you want to choose. And we've got a simple parametric form that maps on the x-axis, the data set size, to the expected error of this model, right? And what do we really expect out of our scaling laws here? So if we're plotting error on the y-axis and data amount on the x-axis, we maybe predict something like a sigmoid for the most part, right? We've got random guessing if you don't have enough data at all. And on the rightmost end, as we approach irreducible error, you have to sort of asymptote out to the irreducible error. And you might expect that there's sort of some transition asymptotically as we go from like nicely reducing error to irreducible error, right? And this plot is actually from the original sort of a scaling laws paper by Hessness in 2017, who I think were the first people to really notice how predictable these relationships were. And so, for language modeling, we see, really nice, clean data scaling laws like this, where the data set size increases and test loss goes down. And, I was talking to you about language models, but actually also this phenomenon holds across many different modalities. It holds in machine translation on the left, speech in the left middle, and object recognition on the right. So across all of these different tasks, what you actually find is a really predictable relationship between log data set size and log of error. And so why is this kind of true? We know that error should be monotone, but what a scaling law says, if you think about it for a moment, right? It says that the asymptotic decay of the error should be polynomial in the data set size, right? That's roughly what the two relationships mean. If that's true, then if you log both sides, you'll get a linear relationship, right? Of course, some of you who are thinking through this already are like, oh yeah, okay, I know why that would be true. But we can work through this in a very, very simple example, right? This is like the most minimal possible example of how you might do this. This isn't even a classification task, but for a moment, let's think about mean estimation, right? Like the most simple possible task. So I'm just going to draw a bunch of points from a Gaussian. And our goal is just to estimate the average, right? Like there's really nothing difficult about this at all. By standard arguments, my error of this estimate is something like sigma squared over n. If I take logs on both sides, right, my log of sort of my excess error here is going to be, negative log n plus 2 log sigma, right? So in general, if I have any relationship that predicts excess error as a function that's polynomial in the data set size, you expect scaling laws. And you're going to get some lovely lectures on learning theory, and they're going to give you exactly these kinds of asymptotic polynomial decays. In fact, you're going to get very specific exponents about those polynomial decays. What is mysterious, I mean, that might be the end of the story, right? But what is mysterious about neural scaling laws of various kinds is that that's not the end of the story. If we have classical models, like you have a realizable classification problem, you expect to get 1 on n, right? If you have like a non-realizable problem, you might expect to get 1 over square root n. Those are very standard rates. Like many of you have probably seen this in your very basic learning theory class. If you take an empirical scaling law that's fitted to the data of how fast error decays with respect to data, what exponents do you actually see? You see nothing like any of those exponents. Typical exponents that people see are something like 0.2 or like 0.1 in the case of neural scaling laws on the right over here. Probably the words that are in the plot are too small for you to see, but you can take my word for it that the exponents here are roughly in the 0.2 to 0.1 range. And that's actually still really quite mysterious. There are some hypotheses about why this might be. One possible hypothesis is that we could take our mean estimation example and we can put it into a non-parametric setting, right? What does that mean? Well, we know that neural networks are performing estimation in some very high dimensional space. If we think about our mental models of neural networks, instead of thinking about them as like simple parametric estimation problems like mean estimation, we might think of them much more like non-parametric estimation problems like kernel smoothing or binning and counting. If that's the case, then what would you expect to see? Well, let's go through a simple example. We have a high dimensional problem of estimating a non-parametric regression problem like this, estimating this f of x of I. And a very naive estimator for this is to cut the space up into boxes and take the empirical mean within each box. You can do a little bit of math and you'll see that in 2 dimensions you'll get 1 over square root n, and in d dimensions you'll get n to the negative 1 on d roughly, right? So any non-parametric estimation problem of this form, you expect to get much slower rates than what I showed you before. And so some people have argued and have attempted to empirically verify that what's really happening with these scaling laws is they're telling you about kind of the intrinsic dimensionality or the data set, or the intrinsic dimensionality of the data as viewed by the neural network. That's really very much an open problem. In case that was a little too low level or the example wasn't explained kind of well enough, maybe the thing that you should remember from this duo of slides is the following idea, right? Scaling laws generally arise due to some form of polynomial rate of learning. The difference with something like a learning theory bound is that these are empirical, experimentally determined objects, right? They're not upper bounds on how fast error should decay. They're actual measured values of how fast error does decay. And what we find is that the slopes are quite different than what we might initially expect from parametric learning. And some people have argued that that slope is connected to the intrinsic dimensionality of data or some other regularization dependent term that we don't yet fully have characterization for. There's no real smoking gun in any of the empirical experiments that have attempted to nail this down. And so I'll leave this as a really interesting sort of empirical observation that sort of is close to but not quite something that we can fully explain with learning theory. But really, the other reason why scaling laws are interesting, one reason why scaling laws are interesting is because, scientifically, it's kind of cool that you can get these really straight lines between log error and log data or log parameter size. But the other reason why there's been so much interest and so much work on scaling laws is because they're very useful for engineering in practice. You might wonder, you're training a huge large language model. You're going to spend, let's say, $5 million on training this model, right? You better hope to get all the hyperparameters right? Like you can't go back and be like, hey, actually, sorry, we got the learning rate wrong, or like we picked the wrong architecture, so your $5 million is gone. So you better hope that you get that right. And so you might wonder, like, are there any systematic tools that people use for trying to build these models at larger scale? And the principle of a scaling law, right? If you have this linear relationship across model scales, what that's saying is that there's a very predictable thing that's happening. You could design models at the small scale and then maybe start to think about what happens at the large scale, right? And so these are very useful engineering objects. I'll talk about some examples here. Maybe you're designing a huge language model and you want to know, should I use a transformer or should I use an RNN, right? That's maybe one question you might have. You might wonder about optimizer. Should we use Atom or should we use SGD, right? So these are very natural questions to have, and you want experimental tools to be able to answer these questions. Another question is resource allocation, right? If you have a fixed amount of time on GPUs, you could do one of two things. You could train really big models for a short amount of time, or you could train really small models for really long amounts of time, right? If you want the best possible model in a fixed compute budget, what's the right thing to do, right? So you want to be able to answer all these kinds of really, actually engineering questions using something more principled than we tried our best, right? So I'm going to start with sort of the second question I asked first about resource allocation. One thing that's really interesting is that scaling laws can be extended into sort of a multivariate setting, and they still continue to hold. So the first motivating question is, what should our model size be given a fixed training budget for our language model, right? So we want to quantitatively understand the relationship between model size, training data size, and downstream performance. And so some people have come up with this object called joint data model scaling laws. The two sort of early citations on this are Rosenfeld and Kaplan, who both show, or who both hypothesize this sort of fairly simple functional form. You can basically try to hypothesize that error is equal to some polynomially decaying term in the data size and some polynomially decaying term in the model size. And the asymptotics for this at least kind of check out if you think about it for a moment, right? Sending data to infinity but fixing model size gives you some irreducible error, right? The M term won't vanish. If you send your model size to infinity but you fix your data size, you're also not going to get to 0 error. The only way to actually get the true irreducible error is to jointly scale model size and data size to infinity, which gets you sort of like a non-parametric neural network limit, and you might hope that eventually gets you the true distribution. One thing that's empirically quite interesting is that this approach gives quite good fits to the error across both the model and the data axes. And one thing that's sort of interesting is if you start to plot these joint trade-offs, what you kind of find is that the best kind of model for a given compute budget is to train a really big model that's not fully converged. If you're kind of often thinking about, once again, like classic sort of machine learning training, what you really want to do is take a model and train it until it's converged. Maybe it's converged in training loss, or maybe it's converged in sort of validation loss or something like that, right? But because we're not in a data-bound setting, but we're in a compute-bound setting for large language models, the thinking is very different, right? You actually want to be training bigger models and then early stopping them once you've run out of your compute budget. And that's exactly what this plot shows here. It's kind of showing on the x-axis the amount of compute that's being brought to bear. The y-axis is the validation loss. And each color is a different model size. And so you see that if you take a really small model, like one of these darker purple ones, and you keep training it for longer and longer, the loss curve basically flattens out very rapidly. And the optimal model to pick is the one that's sort of touching this diagonal line here, which is not necessarily training the smaller models to convergence, right? Like often you actually don't want to be hitting the conversion point for any of the losses for these models. One thing that is an important caution to mention is that scaling laws are basically fitting lines to log-log plots. They can be quite sensitive. And one of the things that people have found, this is a paper by some Google folks, often referred to as the Chinchilla paper. What they did was they sort of did a reanalysis, or they trained some models and fit new scaling laws to a bunch of language models. And what they found was that they found very different scaling behaviors because of the sensitivity of some of the fits. And so what they're showing here is, the dashed line is the prediction from OpenAI's neural sort of scaling language model scaling laws paper, and the solid black line is sort of the scaling laws fit by the reanalysis by these folks at DeepMind. And what they basically claimed was that actually these people, OpenAI and others, were training models that were way too big. They were off by several orders of magnitude because of the errors in their scaling laws. So this is one important caution. A lot of this involves fitting these kinds of linear functions to log-log plots. It is quite difficult to do it in like a statistically stable and sort of robust way. And the upshot of this is that these folks at DeepMind were able to use significantly less compute to train a much better language model than most of the models that came before it that were training models that were sort of far too big. So GPT-3 was 175 billion parameters trained on 300 billion tokens of text. So you can think of this as like a 1.5-ish ratio of data to parameters. Chinchilla was arguing that, in fact, the ratio should be 20-to-1, like you should use 20 tokens to every parameter that you have. And basically, that got them a 70 billion parameter model that was significantly better than everything that came before it. And sort of one side note that I'll add as I go through this slide is that the modern language models that people are building violate this even further. All of these papers about scaling laws, they're about compute optimality. They ask this hypothetical question. Let's say I have this amount of compute, what's the best model I can get? But if you're actually like giving a model to somebody to run, that's the wrong calculus, because a big model costs a lot to run at inference time, right? And so actually most people today, most companies today are building much smaller models than would be predicted as optimal by this Chinchilla scaling law. They're training, let's say, 70 billion parameter models for tens to hundreds of trillions of tokens. They're training for much longer, much smaller models, because that reduces future inference costs. And I was telling you before about all of these interesting architecture decisions that you could make in a more intelligent way using scaling laws. And that's exactly what I'm showing in this slide here. These are taken from the Kaplan paper once again, they show things like on the very left plot, it's showing how many layers do you need in your transformer as you scale things up. If you have only one layer in your transformer, the scaling behavior, this dark purple curve, is way worse than everything else. Whereas once you have enough layers, let's say 6+ layers, there's not really much change in the scaling behavior. And so this might give you confidence that actually we really don't want to train a one-layer transformer, but we can get away with just having a few layers in the transformer. Similarly, LSTMs versus transformers, you see in the middle plot that the scaling behavior is once again pretty different. Transformers behave very nicely in this very nice linear way in this blue line. LSTMs have this constant factor offset. They're above the blue line in essentially all points. So you have no real reason to be using them for this kind of large scale language modeling. And on the very right, you have a scaling analysis of sort of Adam versus SGD, which shows that Adam, which is the dominant optimizer that people use, scales generally much more nicely, right? And so all of these analyses are basically telling you how to make these kinds of algorithmic decisions on the basis of an empirical but somewhat more systematic way than what you might originally do if you were trying to train these models. So scaling laws really, in some ways allow you to extend, beyond just these like scientifically interesting settings. It allows you to engineer things like, pick optimizers or pick architecture choices or pick data versus model size trade-offs using something that's a little bit more intelligent. Okay, so that was scaling. And I now want to talk to you about sort of what this buys you. If we scale up these pre-trained models, they can do all sorts of interesting things. I showed you that fill in the blank slide that I left you with. But we can kind of see language models doing things like making common sense inferences and inferring the beliefs of agents. So if we have a piece of text that shows a person doing a certain thing, like watching a demonstration of a bowling ball, and he's a physicist and so on and so forth, it can model the fact that a person that watches this might have a standard misconception, which is that bowling balls and leaves drop at different rates, and then sort of model that. They can model things like math, right? They've seen tons of math text on archive, and they can now sort of auto-complete things in a way that allows them to solve math problems. And I've already showed you these examples of being able to auto-complete code in sort of quite amazing ways. Other emerging applications include things like medicine and multitask assistance. And where I'm getting to here is that it's kind of obvious at this point that if you have these gigantic pre-trained models, if you put them into the right setting, like you do the right in-context examples, or you have the right sort of prefix that gets you the right conditional, these models have a lot of knowledge in them, right? We can have the right kinds of predictions that can do many kinds of downstream tasks. But in a way, it's very, very hard to use these models, right? It's really hard to just give them sort of an instruction and sort of have them sort of follow it. And sort of there's this big gap that I want to talk to you about next, this post-training gap. If we have a pre-trained language model, it's exceptionally good at completing a sentence, right? If you have Stanford University is located in blank, it can sort of nail that problem. It is really bad at being sort of a general purpose sort of assistant. It's really bad at being a multitask model that can do many tasks without this kind of specialized, what people call prompt engineering. And so how can we go from this autocomplete system to the kinds of kind of very cool multitask prediction system that is ChatGPT? And so that's the part that I want to talk to you about next. So that to motivate this problem, let's take GPT-3. You and I hopefully both agree that GPT-3 is pretty cool. It knows a lot of different things. It's got a lot of world knowledge. But if I take GPT-3 and I ask it to autocomplete the following input, explain the moon landing to a 6-year-old in a few sentences, what will it do? It actually won't respond to that with an answer, right? Often the most likely or a very high probability completion to an input is either paraphrasing it or repeating it. This is just sort of a weird quirk of natural language, I think. And so the completions here is it's going to be explain the theory of gravity to a 6-year-old, explain the theory of relativity to a 6-year-old, right? It's going to be different paraphrases of the original input. And so it's not really following user instructions in any meaningful way. This is a pretty terrible system if what you want to do is have a system that can take in natural language inputs and produce predictions that are consistent with some task that you specify, right? It's not very good at that at all. And so what we're going to do, actually, sorry, I'm gonna dwell on this one more moment here. And so what we want to do here is in some sense have a system that can follow many different tasks, right? Explain the moon landing is some sort of natural language processing task, right? It's like an explanation task, right? You might have a question answering task, like who is the current president of the United States, right? You might have a summarization task, like summarize this article for me, right? And I want a single model to do it all. And so what's going to happen now is, let's go back 15, 20 slides. I told you before that one of the oldest paradigms in pre-training is to take that pre-trained model and fine-tune it for the downstream task. Now what we're going to do is we have a model that we want to do many different downstream tasks at once, right? Not just one downstream task, dozens, maybe hundreds of downstream tasks. So how do we do that? Well, let's do the very naive thing first. The naive thing is to take our pre-trained model and just fine-tune it on many, many tasks all at once. And let's see how well that does. And it turns out that works quite well. This is kind of the start of a lot of what people call sort of multitask fine-tuning or instruction tuning. And the idea is quite simple. You take a language model, you cast a whole bunch of tasks. Let's say you have hundreds to thousands of tasks. You turn them all into natural language inputs and outputs, right? Most tasks can be phrased into some kind of natural language instruction and a response, right? If you have a question answering task, like please answer the following question, ... That's a natural language input. If you want to do a reasoning question, you could say, please answer the following question by reasoning in a step-by-step way. And because these are text in, text out problems, you can take them all as training data, this supervised learning data, for a language model and put them all into this common format, right? Like the key here is everything is text, and so everything can be put into the same model at once. Now, the interesting thing is that if you train on enough of these different tasks, it can start to generalize to new and unseen tasks. If any of you have really read some of the meta-learning literature, there's a very simple sort of analogy to this. You can imagine, normally we think about data distributions. Like we have a task, we have distributions over examples. Now instead, let's think about task distributions. We have a lot of different tasks. We sample a bunch of tasks, and can we generalize to like a held out IID task, right? And it turns out you can. The key thing here, of course, is that the language model is pre-trained. It has very good sample efficiency properties. It can generalize to many new tasks. Like let's say I have a QA task, which is formatted as Q: can Jeffrey Hinton have a conversation with George Washington, ... right? And the interesting thing here is what people have found is that models can often compositionally generalize. In this example, it's combining the ability to do QA with the ability to do reasoning, right? And so in practice, people have found that this thing is quite effective in many, many different ways. In the past year or so, there's been a huge diversity of instruction tuning data sets. FLAN-T5, or the FLAN collection, it was one of the earliest data sets, and that was the example that I was showing you before. But with sort of the release of the Llama model last year by Meta, a lot of people started to sort of think about, can we do interesting kinds of instruction tuning? There's been dozens and dozens of data sets that have been creating these kinds of data sets and testing them. And of course, now that there's a lot of different data sets and a lot of different attempts at creating these data sets, we learned a couple different things about instruction tuning. One of the things is, an empirically effective technique is that, these language models that we have today, like GPT-4, are so good that they can actually be used as data generators. A lot of the most effective pipelines that people use today often generate these kinds of instructions from GPT-4, which, of course, is using sort of leveraging the power of a bigger model to train a smaller model. But the interesting thing here is that it allows you to very systematically test a lot of these hypotheses. Another thing that was interesting is the earliest works in this line of work really used a lot of data. If you look at FLAN-T5 or supernatural instructions, which was one of the earlier works along this line of research, people were using like millions and millions of samples to do this process. Over the last year, people have basically started to realize you actually only need thousands of examples to take a very powerful pre-trained model and have it be a very powerful multitask model like ChatGPT. And that's kind of remarkable in a way, right? Because it means that the ability to sort of interact with people and answer questions or whatever is actually a very easy capability to pull out of a model if you only need like 3,000 samples to fine-tune that into a model. And then finally, because these data sets don't need to be very big, there's been a lot of really interesting and effective crowdsourcing efforts for basically building these kinds of data sets. Open Assistant is a particularly interesting one where a bunch of sort of internet enthusiasts got together and basically wrote these instruction tuning data sets together. And in fact, it's one of the highest quality instruction tuning data sets that are out there. So now we have this instruction fine-tuning step, and that's great because now it makes a huge difference in the behavior of models. Instead of just repeating sort of the instructions, now it will, generally speaking, follow the instructions, give answers, and we can actually leverage the power of the pre-trained model to complete a whole bunch of tasks. But of course, the challenge is that it can be expensive to collect ground truth data. But of course, there's actually much more subtle issues. In a case where you have a correct answer, collecting data and fine-tuning for it is great. But if you have something like, creative generation, you might have subjective differences. It might also be unclear if you can write the best possible creative output, right? I think I can read a piece of text and give it a rating, like, is this good creative writing or not? But I don't think I'm a good creative writer, right? And so it's much harder to generate than to evaluate, and that's one sort of problem. Another problem is that language modeling, it's this cross-entropy loss. That's a great loss for doing generative modeling. It's maybe not the greatest loss if what you're doing, if all you're doing with the model is generating pieces of text, right? If we think about it, there's a mismatch. Generative modeling is asking us to have a distribution that can cover all possible, sort of future continuations of the sequence, but all we need is one really good continuation or a few good continuations in most cases. And so the loss is in some sense a little bit mismatched. It turns out that there's a way to try to bring these two objectives together and align sort of the objective of the language modeling task with what we want to use it in downstream applications. And so that's kind of the next part. So the next part is going to be trying to optimize for human preferences. And this is what often people call RLHF, or reinforcement learning from human feedback. And I'll talk about that a little bit more now. So let's say what we want to do is something like summarization, right? I want to summarize a news article. And of course, I've done instruction fine-tuning. So you've written a few summaries for me, and I fine-tune my model on that. Now my language model can produce summaries, but maybe they're not the best possible summaries. So what I'm going to do is I'm going to have the language model generate a few different summaries for each input. So now there's S1 and S2. These are two potential summaries that have been generated by my language model. And a human rater can come in and let's say rate each of the summaries for how good it is, right? And rating output is a much easier task and maybe an easier task to calibrate than to actually generate a full sequence. Now, if we think about it for a moment, the goal of language modeling, if we're using it in these kind of like chatbot or like task-oriented roles, is actually to maximize this reward, right? We want the human user to be kind of maximally satisfied with the outputs that they're getting, right? So that's this goal. Now we're trying to maximize some reward subject to using the language model as a policy. And hopefully you can see how this is quite a different objective than maximizing log likelihood, which is very much a sort of generative modeling objective. So we've gone from this upstream objective, which is generative modeling, to this downstream objective, which is maximizing rewards. So at a high level, this is exactly this idea that underlies what people often refer to as RLHF in the literature. People call this stands for reinforcement learning from human feedback. And it was originally popularized by some folks at OpenAI who were using this to basically build language models that like better followed instructions, right? So the first step we already talked about, it's this instruction tuning idea of getting a whole bunch of input-output pairs for each task and then fine-tuning the model for it. The second and third steps, the goal here is to maximize a reward, but maybe we don't really know how. So how do we do that technically? Well, this is just a reinforcement learning problem. I hate to say just a reinforcement learning problem because reinforcement learning in language often involves a lot of pain. But conceptually, it is just a reinforcement learning problem. And I'll talk through sort of a really simple version of a reinforcement learning problem. Sort of the classic implementation of this idea is often through what people call PPO. That's an algorithm that is sufficiently complicated that I'm not going to go through here. And I'll go through the simpler alternative that people use today later in this talk. But conceptually, I want you to sort of understand the reinforcement learning process. I'm going to talk about the simple reinforce or policy gradient estimator. So what do we want to do? We want to change the language model parameters to maximize the reward. That's this very first equation here. And of course, we want to do it maybe through gradient descent. We know that's empirically effective. And so we would like to take the update that's shown here in the middle, right? We like to update theta such that it takes a gradient step in the direction of maximizing reward. And what does this? Well, any sort of policy gradient style method will do this, in particular sort of reinforce. And so this is really the one slide overview of this idea. It is actually quite simple. So what we want to do is we'd like to take gradients with respect to the reward. But of course, the challenge here, right? If theta was inside the expectation, life is very easy, right? We would move the gradient inside of the expectation. We would take gradients and we would average. This is exactly stochastic gradient descent in its natural form. The issue, of course, is that the policy, right, the theta is in the sort of the subscript of the expectation, right? So this is in the policy term. And so now what we're going to do is we're going to write out the expectation explicitly, so that's the sum over all possible states or sequences. And we have P of theta times the reward S. That's the expected reward, right? We can push the gradients inside the sum, and we'll get the sum of the rewards multiplied by the gradient of PS. Of course, standard trick in the reinforce algorithm is you basically rewrite this, right? You take the gradient of P theta S, and you write it as the product of P theta S times the gradient of log P theta S. That's the right term of this middle equation here. And we can do that rewriting because of this very nice identity that the gradient of log P theta S is equal to 1 over P theta S times the gradient of P theta S. It's a simple sort of chain rule trick, right? And so because of this, we can now rewrite the very first equation, substituting in the gradient of P theta S. And we can rewrite this as an expectation, right? So the whole point of this exercise was that we wanted to pull out a P theta S term so that we could rewrite this sum as an expectation. And that's exactly what we have at the very bottom here. We've rewritten sort of the policy gradient as an expectation where we sample S hat from P theta S, and then we compute reward times the gradient of log P theta S. So what's the point of this? In a way, you can think about this as when the rewards are high, right? If the rewards are positive, let's say, we're going to take gradients in that direction. If the rewards are negative, we are going to take gradients away from that direction. In many ways, a very intuitive objective or update if you look at it. So that's great. We now have an algorithm that can let us, in principle, optimize any arbitrary non-differentiable reward RS and train our language model. Of course, you might be laughing at that line because in practice, we do not have an algorithm that can let us train language models against arbitrary non-differentiable reward S. But for now, let's pretend that that fiction is true. The issue, of course, we have several other issues. In order to actually do this, we would need to get samples of R of S, these rewards. That turns out to be pretty difficult and terrible because now you have a human in the loop problem, right? We have to have humans continually give us reward signals to update our model, and that can be expensive and slow. So what people do instead is, you can model their preferences. So you first generate a bunch of outputs from the model, you get ratings for their rewards, and you have a neural network that models the rewards themselves. So you have a surrogate reward model, and then you have you optimize the language model against this surrogate reward model. This turns an online reinforcement learning problem into an offline reinforcement learning problem. Another issue is that human judgments can be pretty noisy and miscalibrated. Like, I tell you, oh, this output's a 5. What does that mean? Like, your 5 is probably very different from my 5. And so instead, a pretty common choice that people do is they look at pairwise comparisons. So they'll look at, pairs of examples or tuples of examples and rank them instead of giving absolute judgments. This turns out to be, in practice, a generally effective strategy for data collection. Otherwise, you have to think very carefully about how you normalize reward scores across people, getting you into a little bit of a mess. And so a lot of the leading RLHF algorithms operate directly on these kinds of pairwise comparisons. And so the key thing here, of course, is that once you have these pairwise comparisons, how do you build a reward model? There's a kind of clever choice here, which is that you have a pairwise comparison, and you build sort of a classifier for which one of the two samples is the better sample. And because the classifier internally has a logistic output, right? You have a logistic regressor, you're having an output for each output, you basically have a reward model individually for each sample. Putting this all together, we basically have everything we kind of need. We have a pre-trained model, right, which we have trained at great expense using things like scaling laws to get this very powerful, rich autocomplete system, right? That's the red PT of S. We now have a reward model in which we've shown a bunch of crowd workers, outputs from our model and asked them which one of these two outputs is better. And we've trained a neural network on it, right? So now we can use this trained model as a kind of surrogate reward and optimize against it. And then finally, we have some method of optimizing language models to maximize this reward. And so what we would do is we would then try to optimize our language models against this objective. And so this is the actual RLHF process. And you would optimize this objective that you show here at the bottom, where you've taken the actual reward as computed by the reward model, and you add in a KL divergence penalty, the second term over here. The KL divergence penalty may at first seem like a slightly odd object. What that's basically doing is it's sort of keeping you close to the original pre-trained model. You don't want to deviate too far because the pre-trained model offers some very good inductive biases, and you want to prevent sort of overfitting on your model. So what does that get us overall? So what this does is, if we actually do this kind of reinforcement learning process, you get significant gains. This is from some of the original reinforcement learning from human feedback paper by OpenAI. On the x-axis is models of different sizes. And from the scaling law, where we kind of know bigger models are going to be better in some very predictable way. On the y-axis here is how often human raters preferred the model's outputs to references. So the references are human written. So 50-50 would be something like this model was just as good as a human at writing summaries. And you see that sort of pre-train only, the light blue line, right? It's quite bad at small sizes and only starts getting good once the model becomes big. Even then, it's not super great, right? At 12.9 billion parameters. Instruction fine-tuning, which is the first part of RLHF that I talked to you about before, that's the green line here. And we see significant gains from just doing that process, right? And so now we see that even the small models are doing reasonably well. And as the models get bigger, you slowly approach reference summaries. And sort of the human feedback process, this pairwise rating and reinforcement learning gets you to this yellow line, a really dramatic improvement where you get significant boosts in sort of win rate versus human references that also seem to sort of benefit from scale. And so this really kind of demonstrates much of what you're seeing here. I think this one figure encapsulates a lot of the gains that we've seen sort of out in the open source kind of community as well, that pre-trained models are important. They can solve a lot of tasks if they're big enough. But instruction tuning is really key to getting them to sort of follow tasks and do sort of reasonable things. And an RLHF can give significant win rate gains kind of on top of that. And that was sort of OpenAI study. Many of us, including some of the people in my lab, have been doing kind of follow-up studies, trying to do controlled comparisons of a lot of these algorithms. And for the most part, our conclusions generally match a lot of what the industry labs have published. So just to go through one example here, this was a sort of replication study that some of my students did last year, comparing a lot of the different RLHF algorithms using different kinds of feedback. This is a slight side note, but the rightmost column is using humans to give feedback and using humans to rate. We were also interested in whether models like GPT-4 would be useful in doing this kind of research. So GPT-4 giving feedback and GPT-4 rating, that's the column to the left over there. And what we find is that Llama 7B, which is the very bottom row, that's a reasonably good pre-trained model, but it's actually pretty terrible at following user instructions. It only wins against a baseline model 6.5% of the time. If you instruction tune it, you'll get sort of the model in the middle, this SFT10K model, which wins about 50-50 of the time against a baseline model. And finally, if you apply PPO, which was the reinforcement learning from human feedback algorithm, you'll boost this back up to about 55%, which is an even more significant boost, sort of beating finally the baseline. And so we see exactly this kind of thing happening. Empirically, you might also ask, what does this thing actually do, right? Like you see in all of these charts, like win rates go up. You're like, what is a win rate? What does that mean? We actually see really clear differences in the behavior of these models as we start to do things like RLHF. So at the very top is an example instruction from a data set that we have, which is like, what are the 5 most common causes of stress among people, question mark. If we do instruction fine tuning, we'll get something, something pretty short, like the 5 most common causes of stress among people are work, money, relationships, health, and family, period, right? Very short, very, to the point. If you apply RLHF, what you actually find is, this much longer, this bulleted list description that explains, what's going on. If you've ever wondered kind of why, ChatGPT likes to use bullet points and likes to respond very verbosely, a lot of the research, including ours, have found that people really like to give thumbs up to outputs that contain those properties. So they come often from the RLHF component of these models. Okay, so I've been telling you about how this like RLHF paradigm is really effective, right? This RL idea. At the same time, it's not really magic. There's a lot of limitations to reinforcement learning, especially reward modeling, which is a core component that's used here. Human preferences are extremely unreliable. Chatbots are, if you think about this rating process, imagine someone like flashes 2 long pieces of text in front of you, like 2 answers to a question answering task. And someone asks you, which one's better? You get 30 seconds. It's really hard to be authoritative about which one's actually better. You don't have time to fact check any of those outputs or to really carefully see what's going on. Because of that, often what happens with these RL processes is that it encourages models to be very confident, stylistically good, but may not necessarily encourage factuality. And we've seen sort of many sort of problems with that in issues like sort of hallucinations. There's another sort of interesting technical problem that people have identified called over-optimization. So one of the things that people have observed, especially folks like OpenAI have been talking about for a while, is this idea that on the x-axis of this plot, you see how well you've succeeded at your RL task, right? So this is how far your policy is from your base policy. And on the y-axis is how good humans think the actual model is. And you see this very characteristic unimodal curve where initially, as you're doing reinforcement learning, your model gets better and better and better because you're obviously maximizing rewards, but actually you're not really maximizing true rewards. You're maximizing surrogate rewards where you fitted this neural network predictor. And because of that, after a certain point, actually the human preferences start to come back down. So if you over-aggressively optimize against your reward model, you've overfitted to your sort of surrogate reward rather than actually optimize true human reward. And because of all of these reasons, one of the things that some people have done and have really caught on is ideas that remove reinforcement learning from RLHF. And one example of this is a popular algorithm called DPO, which basically, instead of having a reward model, essentially makes a non-parametric approximation to the reward model, and then they show that you can analytically remove the reward model from the process and get a sort of not quite closed form update, but you can write down the gradients for the objective in a way that avoids algorithms like PPO entirely. And almost all the people basically doing RLHF, especially in the open source or academic community, use this algorithm now since it's much, much more stable and easier to work with than PPO. Okay, RLHF is kind of an interesting topic. I think for a long time, people didn't really think reinforcement learning was going to have any sort of impact on sort of natural language processing. There was sort of a period of excitement, I think around 2015 or 16, and then the lack of results back then sort of killed RL in NLP for a while. But now I think it's really come back with RLHF and all of these kinds of interesting algorithms and interesting results. The interesting direction for a lot of these industry companies is that they're actually looking towards sort of the data aspect of these problems rather than the algorithms aspect. For example, Anthropic, an AI company, has been thinking a lot about, can we generate these pairwise comparisons automatically from LLMs themselves? And others have been thinking about using instruction tuning, where basically models generate their own instruction tuning data in a particular structured way. And so there's going to be a lot of different sort of things that are solvable versus not solvable. It's a very much open question of what this class of algorithms can actually end up doing. Okay, so this is basically all of the how do you build a language model part of this lecture, which I think is sort of core understanding and knowledge for even talking about and reasoning about language models. But this is of course machine learning summer school, and so I wanted to talk a little bit about some aspects where we might be able to intersect interesting ideas from statistics and machine learning with language modeling, and hopefully have a little bit more sort of precise things to say that making neural networks bigger makes them better. So to start with, I want to now dwell on slightly the problems with language models. Language models work really well, and they continue to work really well when you scale them up. But there's been some persistent problems with their capabilities and their use. And I think I'll bucket them under generally trustworthiness. It's kind of hard to have language models be trustworthy. In many different ways. They hallucinate very aggressively. Many of you may have seen this Air Canada example from recently. If not, it is quite the amusing story. So I'll tell you. Air Canada had a chatbot. Someone asked Air Canada chatbot whether they could get a reimbursement for a certain kind of flight. Air Canada chatbot said, yeah, sure, you can get a reimbursement. And of course, this person took the flight, didn't get reimbursed, sued Air Canada. And then Air Canada, in a very entertaining defense, said the chatbot is its own entity. We're not responsible for its outputs. But they were responsible for their own outputs. They lost that legal case. So hallucinations, very important for the actual use of these models. Another issue is misuse and spam, right? Language models help us generate human-like texts. They also maybe help us do things like cheat on exams and assignments. That's maybe not so great. Finally, pre-training is great because it ingests the whole internet, not quite the whole internet, but a lot of the internet. But really, actually, if you ingest a lot of the internet, it turns out that the internet contains a lot of test sets, and you need the test sets to be clean in order to do evaluations, right? And so there's this final sort of issue that we don't really even know how to evaluate these things cleanly. And all of these problems are kind of high stakes in a way. We would like to have some more precise guarantees than to say, oh yeah, the model works, okay. And so this is a place where I think a lot of the statistical guarantees and a lot of stats ML really maybe comes into being. So I want to talk about sort of 3 different examples, starting with this idea of controlling hallucinations a little bit better. So, given the Air Canada example, we would like to have a language model that doesn't make up facts. That seems like it would be nice. But having a system that never fails is a pipe dream, right? None of us have ever made a machine learning model that never fails. But it may be possible to get some sort of high probability guarantees, right? Like with high probability, I would like to guarantee to you that my model is correct with some given level of accuracy. That seems maybe possible. And so the contract is you're going to give me a bunch of inputs, and I'm going to tell you that on those inputs, 95% of the time my outputs will be correct. And of course, this is difficult because language models are these enormous neural black boxes, right? Like we don't really know how to precisely control their behavior. People are working on ways of doing that, but it has thus far been very, very difficult to build language models that are both high performance and precisely controllable. And so we might turn to a very different kind of tool to solve these problems. One place where we have had success in the past is conformal prediction, which has been sort of an area of statistics that has had this very interesting approach where you have some inputs, you have a deep neural network that you have very little, if not no control over. And what you would like to do is to give a formal frequentist guarantee or your frequentist-like guarantee, and to say 95% of the time the true response or the true response is within sort of this set that I give you, right? That would be very nice. Conformal prediction gives you something very close to that. It gives you what people call a marginal coverage guarantee. on arbitrary black box models. And so that's pretty cool. It means that maybe you can use some black boxes and put some wrappers around it and be able to get something a little bit more precise than you had before. And it's been somewhat successful. There's been a couple of people at Berkeley really pushing this line of research and using it in things like scientific discovery. Of course, this doesn't really type check. Conformal prediction is great because it works on black box models, but it's an uncertainty quantification method, not a method to guarantee the factuality of our outputs. But one thing that's kind of interesting is if we think about for a moment on what language models output, they output sequences. And sequences are objects that are much richer than just point predictions. For example, a language model, if you ask it, like, where was Abe Lincoln born, right? You can give many different kinds of answers. You could give on a farm in Frankfort, Kentucky. That one's wrong because Frankfurt is actually false. Or I could back off and I could just say Kentucky. That would be correct, right? That would be correct if I removed enough facts. It turns out this has kind of the flavors of an uncertainty quantification problem, right? I could add a lot of details, be very specific, and you can think about that specific output as being like a really narrow uncertainty set. Or I could just back off and say very little. I could be like, he was born somewhere in the United States. That's a very big uncertainty set, right? And so actually there's this kind of cute correspondence between uncertainty quantification and correctness. You could basically associate each language model output with sort of a confidence set. And you can say that if my true answer is in this confidence set, the original answer must be correct using various forms of entail. And so this actually just turns into this fun little algorithm where you basically take language model outputs and you sort of make them less specific in a very structured way. So I'm going to black box some of the objects here. Once again, this will work with any black box implementation of these ideas. You have an output Y0 from a language model. You have a black box that makes them increasingly less specific. And you can score them each with a confidence measure S. And you can use conformal prediction to pick the right level of less specific in order to guarantee the correctness of your output. And so at inference time, what you're doing is you're basically removing sort of uncertain details until you're basically sure that whatever you're saying remains correct. And since there's a very clear correspondence between conformal sort of uncertainty sets and the correctness of outputs, you can actually just turn the standard conformal machinery and get correctness outputs guarantees for language models using just conformal prediction ideas. And so we have a theorem that basically says our language model is correct with a given level of probability. Do we actually attain that correctness guarantee? So the x-axis here is the factuality level that we would like from a language model. The y-axis here is the empirical frequency of how factual the language model is. And the two dashed lines are sort of the outer limits, the upper and lower bounds proved in our theorem. And my student made fun of me for this because I said, oh, maybe we can plot sort of the factuality levels. He said, we have bounds. Why do we need to plot the outcome of bounds? You can see in here that our theorem is correct. And one of the cool things is that we can take this to somewhat challenging long form factuality settings where you take GPT-4, you ask it to write biographies about some obscure people, it'll really aggressively hallucinate. In our case, almost 0% of the outputs are free of hallucinations. And you can apply this kind of conformal prediction inspired approach. And you can basically get to something like 80% correct from almost 0% correct without removing too much. And you can kind of visually see this here. You don't have to read the passages. But on the left is the outputs from the original language model. All the falsehoods are colored in red. And on the right-hand side is basically what happens after you remove some of these uncertain details using conformal prediction. And you basically get something that removes a lot of the falsehoods. And we can sort of check and see that this attains the correct factuality guarantee, which is about 80% is what I think we targeted. So that was one way of using these kinds of ideas from statistical learning and statistical inference like conformal prediction to be able to say something quite precise about the outputs of language models. And so that's kind of cool. Now I want to talk about a different kind of setting. I want to talk about misuse. Maybe you're passing off language model outputs as your own, or maybe someone's polluting the internet with language model outputs, and we'd like to detect and potentially remove it. There's been an emerging idea of using watermarks for language models, originally proposed by Kirchenbauer and also Scott Aronson. And that allows us to trace text that are generated by language models. But of course, there's some challenges. Language model generated texts watermarks induce distortions in language models generated text, because injecting a watermark requires you to change how language models generate text. And then, if you want it to be not low distortion, then they're often not robust. Just to give you a sense, if you haven't heard of or thought about language model watermarking before, the idea is kind of cool. And there's a lot of interesting stats tricks you can apply here. How do language models generate text, right? We have a probabilistic model, right? And we generate from that probabilistic model. And so often we're generating text stochastically, right? We have a language model. It has a prefix. It has continuations. And metaphorically, there's a dice roll to determine which of the continuations we choose, right? Well, because there's a dice roll here, there's actually room for us to intervene in this process and sort of load the dice, right? I have a secret key that makes me sort of change which dice rolls are more or less likely. And because of that, when I have the secret key, I can tell whether or not the text was generated by this language model. And if you don't have the secret key, you can't really tell the tool, right? So they make outputs very detectable. And so the key idea here is that you can develop these kinds of distortion-free and robust watermarks. This is a kind of cute idea originally from Scott Aronson and with a variation from my co-authors, Rohith and Percy and John, where what you do is you sample this very big block of random numbers called the key, that's the Xi, and you sample according to this min of the negative of the log of Xi over P. And this is a very odd-looking object, but if you remember sort of your basic probability, this is actually a very easy to understand object. Xi is a uniform. Negative log of a uniform is an exponential. Dividing an exponential by a number gives you an exponential with rate P of I. And the minimum of k different exponentials with different rates is actually proportional to that rate function, right? And so that sampling process actually gives you something that's proportional to sampling from P of I, or exactly sampling from P of I. And so this is distortion free. If you don't know the key, you can't tell that this was generated by this process, or if I honestly sampled from P of I. Detection is also pretty easy. You can basically take your output sequence and do sequence alignment against the key, right? Because the key basically gives you detectable spikes in which words are more or less likely. And of course, since we're doing Levenshtein alignment, this is a robust thing to do. There's been a lot of really interesting things that people have done with watermarks. I just want to highlight them because I think they may be of interest to you all. People have done things like randomly separate the vocabulary space into a green word, which is good, or red word, which is bad, and slightly upweight the green words in a way that can later be detected by hypothesis testing. Other people have used pseudo-random functions of the previous K tokens and sort of adjusting that in a way to make them distortion-free. The upshot of this is that if you're running a language model with a watermark in kind of a high entropy context, that is, there's many possible continuations, you get really powerful watermarks, right? Hypothesis tests sort of increase in power exponentially. And so if you have roughly 20 tokens or more, you're getting sort of vanishingly small p-values for detecting model-generated text, which is pretty cool. And it's also robust to random deletions, although not to adversarial attacks. People have shown that pretty clearly. The final thing I want to end with is kind of this interesting idea about evaluations. I've been harping on how pre-training is so powerful because it trains on enormous amounts of data. But this is actually also a really big problem because if you want to evaluate a language model, how do you know that your evaluation set wasn't somewhere in the pre-training data of a language model, right? And sort of a core thing about machine learning is that we keep our test sets separate from our training sets. And sort of it's really hard to know. And people have found some credible evidence that there's some contamination on some of the models. On the left is sort of a fun Twitter post by Horace He, who showed that when GPT-4 came out, there was something a little bit weird about its performance. It was 100% accurate on pre-2021 code forces problems. And then it was 0 out of 10 on post-2021 code forces problems. And he was like, isn't that suspicious? And yeah, that is a little bit suspicious. On the right is Susan Zhang, who when Phi 1.5, which is another language model, came out, she showed that if you took a benchmark, chopped it in half, so you basically took the first half of the questions and you ran the language model on it, it happened to autocomplete sort of the rest of the question. And you're like, isn't that suspicious? And you're like, yeah, maybe that's also suspicious. But all these are very deeply heuristic tests, right? There's nothing really smoking gun about a language model being able to autocomplete things. And so it would be really interesting, at least scientifically, if you could detect these kinds of test set contaminations in a very provable, precise way without looking at the training data set. And so I'll pose this as a statistical testing problem. You give me a test set and a language model, and I'm going to return to you a statistical hypothesis test that has a really precise false positive guarantee. So just like a t-test or any kind of statistical test, I'm going to guarantee that my false positive rate is at most alpha. And the kind of cool thing is that there's aspects of this problem that lets you use ideas like exchangeability. So if we think about it, most test sets in machine learning are IID or exchangeable. You can shuffle the order of these test sets, and the distribution would be exactly the same. And because of that, right, there's no, in some sense, preferred ordering to any data set. And one thing that would be cool is if a language model has a preference for an ordering that appears, let's say, on GitHub or somewhere public, that preference could only have come from sort of seeing the data set, right? And so the key idea is that any preference for the canonical ordering for a data set must have come from contamination because of the exchangeability property of the data set. And you can show this formally that for any exchangeable data set, the log probs themselves must have the same distribution under arbitrary shufflings. And you could turn this into a pretty clear p-value, which is a test for contamination, in which you just shuffle the data set and you repeatedly measure log probabilities, and you ask, does the model assign much higher probabilities to the original ordering than to the shuffled orderings? And turns out this test actually kind of works, which is cool, given that we have no access to the training data set and we're giving you really precise guarantees. We trained a couple 1.4 billion parameter models, and we injected some test sets into this data set with some known duplication rates. The dupe count basically tells you how many times we put in the test set, and we have different p-values with different kind of algorithms. I didn't tell you about sharded p-values, but you can ignore that for the purpose of this lecture. Basically, what this shows is that for anything that appears more than 10 times in the pre-training data set, we can really, really precisely detect its presence in the pre-training data set. And you might be curious, can we go lower on the duplication rate? Unfortunately, the answer is no. No algorithm I know of can reliably detect any amount of data, including test sets, that appear only once in a pre-training data set. That's another interesting empirical fact about memorization in large language models. So, between 2 to 4 duplicates, we can start to detect it, but not otherwise. Sort of in the wild, one of the things is we don't really see pervasive contamination. If everyone was training on tons of different test sets, we'd expect to see this table with really low p-values, but that's not the case. There's only really one p-value that passes multiple hypothesis testing correction, and that's Mistral 7b on ARC. We do also see that Mistral and Llama both have very low MMLU p-values, which is kind of interesting because that's consistent with Llama 2's own technical report. Okay, so that's all I've got. There are a few key ideas in the second part that I want you to remember. For pre-training, right, in some sense, pre-training is the biggest empirical thing to happen in NLP, and it's what powers all of this large language model stuff. And the technical empirical component of pre-training, I think, is things like scaling laws, in addition to sort of the systems optimization that makes scaling possible. For post-training, that's the piece that allows people to sort of interact with language models and use them in many effective ways across tasks. And that involves RLHF in instruction tuning. And now we're beginning to gain an understanding of how those things work. Finally, there was the last section where I told you a little bit about some interesting things that you can do that sort of intersect a lot of this like statistical ideas in large language models. And so there's a lot of really interesting new problems that arise with language models that are actually relevant and interesting. Thanks. Happy to take questions.